Our research presented in this paper aims to support a multi-user system which will provide data privacy, integrity, and also transparency for different type of the operations. At the same time, it will also achieve the practical performance. So our first author is Daniel. He is not able to travel, but he is available in Slack. So you can also raise questions regarding our research in the Slack channel. There are various data services available today. The companies will gather the data from users and they will perform various computations. And for example, smart grid, the operators may need to answer the queries from their users, like what is the total energy being used in the area, what will be the average and the standard deviation, what will be the maximum among the residential users, as well as what is the certain percentage of quantiles in that area being served by the smart grid provider. There are also other use cases for providing the data services. For example, the congestion pricing, like ERP, electronic load pricing system being used in Singapore. It is used for the server to provide the car owner how many cars crossed a certain gantry, and each user account corresponds to a car and a gantry combination, and the value will represent the number of times a specific car crossed the gantry in a certain time slot. In another example for the digital advertising, the platform operator, like for example Google Ads, may need to provide to the advertiser on the number of clicks for the given advertisement on the being placed on that Google platform. So a major challenge in providing data services is to prevent cheating, because companies may have financial incentive to cheat. So, for example, the server may want to exaggerate peak demand in a smart grid in order to charge higher rate, or may misrepresent the number of clicks to advertisers to steal profit. So we need to guarantee the following requirements for providing the data service. The first is about the data integrity, which means the data will not be tampered with when the data service is provided. The second is about the transparency, to make sure computations on the data will be performed correctly. The third is about the data privacy, to make sure that users cannot view the data value of other users. And there's another requirement is about efficiency, to make sure that it will be able to support a rich set of operations like sums or quantiles being effectively. So there are different approaches to provide data services. We can see two naive solutions. One is to put all the data on a company's server, which will provide a strong privacy, but on the other hand, it will sacrifice transparency because users will not be able to verify the result of the query. And there's another naive solution is to put all data being public, which can support the transparency, but will compromise the privacy, because any user can see all other users the data. There are other approaches also being proposed in the literature. For example, the limited query support using the transparency logs. Those are included like the certificate transparency and the CONIKS. Those systems can only support lookup queries. Very limited types of the queries are being supported. Another work is about a proof of liability, which mainly used in the cryptocurrency context and only support sums and lookup. And there's also work to support the single user, like the authenticated database, which included the IntegriDB and also FalconDB, but they cannot hide data between the users. Here we propose a tab which will not only support sums and lookups, but also other type of the operations like the minimum, maximum, the quantiles, and also sums of the high statistical moments. This is the system model being proposed, and there are three players in this system, including the users, the server, and also the auditors. The users will monitor their data values and also perform queries to the server. And users can also check if the values are being reported by the server, whether they are correct or not. If it's not correct, then users can report the misbehavior of the server to a regulator. And a server will build the data structure for the data being collected from users, and also generate the corresponding response based on the query issued by the user, and also provide the proofs. And the auditor will check the data structure to see if there's the data is only being added and there's no modification and also removal of the data using the Merkle2. So in our system, there are two layers of the data structure being defined. The first layer is about the chronological prefix tree, and second layer is about the sorted sum tree. And each user can only have one value per time slot, but a single person can control multiple users. Here, we assume that if a server with the ability to create infinite dummy users with too many fake accounts being created would be noticeable to the auditors and the regulator. For the first layer in our system is the chronological prefix tree, and the user will have the attributes, for example, the neighborhood or the consumer type in a smart grid. And we assume the space of the possible attributes is not too large, so that each combination of attributes can be mapped to a prefix tree node. And because we only add new entries to the right in the prefix tree, cost of an auditor verification that to check there's no data is modified or deleted is O log n, where the n is the number of the time slots since the beginning of the operation of this service. The second layer of our structure, data structure is the sorted sum tree. And it will store the additively homomorphic components, and the leaf will contain the user value and the moments, because these are needed to compute the statics. And the nodes above the leaves will store the sums of the underlying values. This works because of the additive homomorphism. For the commitment scheme, we use a Pearson commitment with elliptic curves. And we also use bulletproof for zero-knowledge random range proofs. So the sum tree's leaf will be stored with small values on the left, and the larger ones will be on the right. Here, the auditors can verify that one entry is greater than the other one without revealing the underlying values. Our experiments demonstrate that the server can prove the various queries being collected efficiently, including the sum and average using the sum tree roots, and minimum, maximum, and the quantiles using zero-knowledge proof, and also the sorted leaf structure. And we did the experiment on the Amazon machine, and it demonstrated that for a smart grid with 1.8 million users and 100 sum trees and time slots, it will take less than 5 minutes to update the tree. So the maximum audit volume here can support as much as 360,000 values per hour. Okay, in conclusion, our tab system use 2 layers of tree structure and zero-knowledge proofs. And it guarantees integrity, transparency, and privacy. And the verifiable log with rich query support, including the sum, variance, and quantiles. There are some future work to be explored. One is about to provide the to support more query types. For example, we can prove the rank collision using the zero-knowledge proof. So this one we will implement in the future. And the second is about improvement of the efficiency when most data values are zero. For example, in the congestion pricing, many entries are zero. And so we can improve the efficiency for such kind of the use cases. And the third possible the future work is to implement extension to differential privacy. So we can prove the value of the sensitivity using zero-knowledge proof, and also prove the difference between the query result and the true value is smaller than the sensitivity using another zero proof. So that's all for my presentation. Thank you very much.